And talking about energy storage, lithium-ion batteries, one.
Next Friday.
Next Friday. So lithium batteries.
Thank you, Joe. Introduction. So I'm Chunmei from Unreal, and this is the first talk about energy storage. And actually, when I take this title and I feel, wow, this is a really broad title, I couldn't finish in only 2 talks. So I decided to limit this talk to the lithium battery. So in this topic, I will first just a brief introduction on what's energy storage, why we need this energy storage, especially for the great stationary level, large-scale stationary energy storage, all the portable device. And next, I will mention several electrochemical energy storage. And finally, I will limit it to the lithium battery. So for your convenience, and this is outline of this presentation. And so I will talk about the electrical energy storage and the advantage of electrical chemical energy. So I will cover what's the benefits and what's the state-of-art technology. And on the lithium battery, and I will talk about the history of this lithium battery, especially for the current available lithium battery technologies. And also I will mention some state-of-art technology and some startups and Unreal. And finally, I will touch the challenge of lithium battery. I hope this talk can inspire you interest and passion in this field and help our science at some level in the future. So the first, the topic will be why we need energy storage. So this is slide, and I make this picture just to inspire, and it's very important that we need energy storage because we need to power our portable electronic devices. And then we want to reduce the greenhouse gas and save this earth. And this is I got from the one book, and they said every kilowatt of electricity generated by burning coal produces an average of 1 kilogram carbon dioxide emission. So that's the reason why we need to use renewable energy. But natural power always gives some intermittence, it's weather dependent. So that is the reason we need energy storage to store those renewable power and to deliver to the customer and end users. So this is the picture and from California ISO, the water utility in California. And this is from Spain, and both is show how the natural power deliver those electricity. So this is only in the 24 hours. You can see this wind power varies every minute, and of course, it's every hour is have a different power output. And for this solar panel, and they give electricity, it also depends on weather. So on a cloudy day, they have very low output, and the sunny day, they have the really good the output to the grid. So in case in order to give the very reliable electricity, especially when you integrate into the grid, you need to stabilize those electricity. Otherwise, we have to reduce the quality of the grid. So that's why, and we need energy storage. And secondly, and those solar panel and wind farmer is far from the busy cities. And we need to transmit those electricity and transfer those electricity to the end user. So the energy storage will also help those transmission. So for the next one, and I will show the energy storage type. Why we need different energy storage technology? Because each energy storage have different requirements. For example, if you want to use a great reliability and quality, we need this have a really high gravimetric energy density, so that you can store kilowatt, kilowatt electricity. And also it has to be very cheap. Otherwise, the electricity fee will go high. And easy maintenance, because many energy storage will combined to the wind farm is far from the busy cities, and so we don't want to keep them maintenance every hour, and also need a long lifetime and the safety, of course. But for the power transportation vehicle applications, safety is the first priority. And we don't want to sit on the barn during driving. And we definitely need a safe battery, and also give a long range and like a 300 mileage and per each charge. And also we need a high volumetric density. So it's different from the gravimetric density. Volumetric density because the car has limited space. And we don't want to drive drunk truck and then have the battery in the carriages. So we need a very high volumetric energy density battery. And this is came to very challenging. I will talk about later. And also high power. That means you can speed up the car very easily, and also you can charge the car in the second. Will be in the future, but currently the charger car usually take the 8 hours or overnight. And of course the low cost, that will encourage customer buy the electrical car and reduce greenhouse gas emission, right? And of course the electronic devices, this one is already widely used, I think in this particular applications, there's no much very challenging issue because as long as you have the enough battery can give you some like a daytime user, it should be available. And for this, I got this picture from April, so from one utility, and I think that this is really good to give you an overview of this energy storage application. So from the large-scale renewables to the residential areas. And they have the several steps. So energy storage will locate each steps. So from the energy storage wind farm and solar panel, and to the substation transmission, and then go to the residential. So, and they'll include the distribution and transmission. And once you use the car and you kind of distribute the renewable energy, and then you use energy storage at home and the building, and to smart to manage those electricity. And this shows the current available energy storage technologies. And there is several types, but I want to mention only 2 types, and 3 types actually. One is the electrochemical energy storage, whereas this PHS, so pump hydro energy storage, and compressed air energy storage. And these two need a high requirement on the location. And for the electrochemical energy storage, it has a lot of advantage. First is pollution-free relatively, and also is a quick response, because once you want to control and manage frequency on the grid, you need a very quick response. And also they have a low requirement for the locations. And finally, this is very flexible. So if you want to add more battery, you can get large-scale energy storage capacity. And once you want to only like in the car or by the home, and you can just have the small module to provide the electricity. So this is why the electrochemical energy storage has its own advantage compared other geographic energy storage. So in the electrical energy storage, there's several types available for the large-scale energy storage. First is, we know this is a nickel metal hydride. This one is traditional battery. It's extensively used in the portable electronics, and also recently is on the Prius, so the car, the hybrid vehicle car. And also the lithium battery, and the other is sodium battery. They need melting sodium in the tank, and so give the high power. And the top one, this is flow batteries. This one is very interesting because this kind of divide the capacity and the power, because you store the energy into the external tank. So I will talk about the detail about this flow battery later. So on the lithium battery, and we have I will talk about at the end of this talk. And besides those batteries, there has also capacities that will give the high power. So once you combine capacity and the battery, you can ensure the energy and the power. So this is So this is for the several types of electrochemical energy. And this graph shows the capacity versus the specific energy. So this is power versus energy. And we can see the lithium battery has the highest specific energy density compared to other chemistry in this type of energy storage. And also, and I want to show here, so this is from the Nokia Mobile, and this is in the 2008. And he gave the speech in the one conference, and he said this battery still presents the most lagging technology and are the most frequently source of user frustration. And so that's the reason why we need to improve this technology and enhance the capacity and the power. And this is a comparison between those very widely used batteries. So first of all, lead acid. This one has pretty low capacity, but its theoretical capacity actually is much higher than this this commercial capacity. The theoretical around 168 milliampere per gram. But actually, when you see this specific energy in the car or in the real battery is really low, because this lead is they have to put a lot of accessories into this battery package. That is enable this lead acid battery rechargeable. And recently, technology they called advanced lead acid can improve this a lot. And so that's why there's advanced lead acid battery actually is jump here from the initial here to here, because they replace the lead with carbon, and that is reduce the weight of this material. Once you reduce weight, that means you increase the capacity. So that is lead acid, and other nickel batteries have a really low specific energy, and the power is fine. But the thing is, they need some very expensive metal and toxic metal, and the voltage is pretty low compared to lithium battery. The lithium battery is currently we can achieve 250 in the battery package. And the DOE goal of this year is we want to reach the, not this year, it's next year, 300. And that because we already have some new anode and cathode. And the specific power, this range is also depends on the design of this battery architectures. And the cycle life is also depends on the engineering. So besides of chemistry, engineering of the packaging of this battery is also very important. And the energy efficiency is quite high because the lithium ion is light metal, and they can move freely into the structure without destroy structure. So efficiency is much higher than other kind of other electrochemical energy storage. So this one is major development in the electrochemical batteries. And this is the first they found the zinc, and they put the zinc and copper, and then they make this voltaic pipe, so can give the portable device have some electricity. And then they have the lead acid, and further they have a nickel metal hydride. And then the Whittingham in the science paper, and they find the interconnection, not find it, so he developed this interconnection reaction. This is the foundation of the currently lithium battery. So most of the lithium battery use the intercalation reaction. That means is lithium is go into the structure and then come out without disturb this initial structure. So all of the structure keep the original arrangement, and the lithium go in and go out. This is called the intercalation reaction. And John good enough find this nickel cobalt oxide that make the Sony have this commercial, the first generation lithium battery. And later, actually, John good enough found the lithium iron phosphate. That is the currently popular cathode for the lithium battery. And but when I look at the literature, I found this actually this we should the battery development of the battery should date to the ancient time, and because when they the scientists find that this one is from the I think it's from Baghdad, close to the yeah, it's called the Baghdad batteries. And this one is 2,000 years old, and although there's no confirmation what this for, but it looked like look like a lemon battery, and I got from the I think if you take the electrochemistry, lemon battery is the first experimental you should prepare. So they found this iron rod, and then they found this copper cylinder, copper wires. And then they found some the open here, and so they can put the stopper on the top and put the iron rods inside. So iron will react and lose the electron. And then they put some acidic solution into this vase, and they found that they put some grape juice or wine, and anyway with some proton available in this solution. And so the hydrogen will release some proton will release hydrogen. So this is exactly the same mechanism of this lemon battery. So that is also represent the components of battery. So they include the cathode anode, two terminals with different potential, and embed into the electrolyte with some ions can neutral the electricity, and also separator to separate these terminals, not a short circuit inside. And then this is why we can design the battery, use different chemistry. And we definitely want the two terminal has different potential. And so the potential difference, and also how you can make this battery from a primary battery to the rechargeable battery. And how you can make this rechargeable is, so primary battery like a lemon battery is easy to make, but how you can rechargeable. So this is, we talk about the intercalation reaction later. But for this potential table, and for example, this is lithium, and then this is oxygen. So that means they can give like above 3 volts. Is higher than the nickel metal hydride battery. And you just combine these two chemistry half reaction, then you can give the 3.4 volts. So it's also this equation we always use for the electrochemistry to predict what's the voltage you can get from these two different potential. And this is look like easy, but once you talk about the battery, it's not that easy because you don't use that simple reactions. The reaction always include the complex, and also the electrolyte is not like we cannot use the aqueous solution. So for example, this one is oxygen in basic solution, but we have to remember this hydrogen evolution is the window is much small, much narrow than the lithium. So you cannot use aqueous electrolyte in this lithium system. And okay, so from now on, I will take several examples of this for the electrochemical battery. So as I talked before, this flow battery is very interesting, and because they divide the capacity, energy, and power. So then you can give as much as energy as long as you have large space to store those tanks. And this flow battery chemistry is also not that hard. And this is several chemistry, half a potential. And you can do the combination, and then you can get the different potential. And basically, you have 2 tanks. And so you can store the different couple of half reactions. And in this case, 4+ and 5+, and this positive, that means cathode part, and then the 2+ to 3+ into and this anode part, and then you flow those. So as long as you have enough solution flowing into this chamber, and the reaction electron and ions flow in the circuit and inside, and then you can deliver the energy. So this is a battery, but this one is limited into by the aqueous solution. So most of the all of the vanadium redox flow battery currently use in the aqueous solution. So that means you cannot above 1.6 or 1.7. And and also this capacity is also limited by the overall capacity is limited by the concentration, the saturated concentration of this solution. And that means because of the vanadium sulfate and other material can precipitate from this solution. So that means you cannot get a very high concentration. So that means you cannot use the small tank and with a high concentration solution. You have to have the large tank and have the low concentration. It's a high concentration, they cannot allow this redox flow battery rechargeable or lifetime is not good. So for the this one is lead acid battery. This one also uses aqueous electrolyte. That means it's not above the 1.6 or 1.7. But the interesting thing, this lead acid actually can give a 2.1 volts, and it's because of some overpotential. And then they can give a higher voltage than the other aqueous system. And in this lead acid, as I mentioned before, the reality is this lead acid cannot give a much high capacity, cannot give the theoretical capacity, because they need a lot of accessories, like this one, grid plate. So you have to put this grid like a mesh on this part, and then laminate the lead or lead oxide, and then put the separator and put another grid plate and put the lead oxide. So this is many kind of, so each part needs some grid plate. So that means that they increase the package weight and reduce the overall capacity. And the chemistry is from lead to the lead 2+. Usually they use sulfuric acid in this system. So they can get the overall side reaction, zero reaction is lead and lead oxide to the lead sulfate. And again, this one is limited by the weight, and so the currently available, advanced lead acid battery, they replace this lead and by the carbon. So that means they bring some capacity, super capacity, so they call it ultra battery. And that means there's not only this electrochemistry reaction, but also some absorption, disabsorption reaction also going on this lead battery. And this one is widely used in the car and it's most of the powerful electrochemical battery back to the 10 years ago. And currently, once this advanced lead acid battery invented, and I think that this lead acid battery will go on in this area. And so finally, I will go to the lithium battery. So this one cartoon shows how this works. And so now it's charger step. So lithium removed from this cathode and into the graphite. So this one shows both of the layer structure. This is very easy to understand because we talk about intercalation, insert. So once the ions insert in this structure, and layer structure is very straightforward for the lithium come in and release. So for example, this part is a layer metal oxide. For example, lithium cobalt oxide is very traditional, very famous cathode material. And this part is graphite. And once we didn't use the lithium metal, and because there's other issue about lithium metal, graphite actually finally make this battery commercial and safe. And during the discharge and the lithium get into this cathode, and then during the charge, lithium released from this cathode. And so I have to mention these two two scientists, two professors actually, in this area. The first is Professor Stanley Whittingham, and from Binghamton University, and he found this intercalation reaction, and he gave the first generation of this lithium battery, vanadium sulfide. So at that moment, I think it's 1980s, mobile, they call it mobile energy, the Exxon. So they invest this research, and they give the first generation of battery. and use the titanium sulfate. This one is ideal layer structure. This is a very interesting material. This material, I think, is have both ionic conducting and also has a high electroconductivity. So it's just like even the ionic conductivity higher than graphite. And later, Professor John put enough and found the lithium cobalt oxide is really good cathode material because they also have layer structure, and lithium can go in and out. And then this is finally make this commercialization of the lithium battery with graphite as anode. And later, one thought, I think it's 80s, and he further found this lithium iron phosphate. This one is a kind of open mine because this one is not a layer structure, it's olivine structure. And those lithium ions actually sit in the three-dimension structure. But believe it or not, this lithium can also freely move from the structure and come in and get in and release. So, and this is talk about the materials for the lithium battery. And as mentioned previous slide, and carbon lithium cobalt oxide and lithium iron phosphate, and both can let the lithium intercalate into the structure. And so this is this is graphite, and this one is lithium cobalt oxide. And also the cobalt is very toxic and expensive. So that's why the scientists use a different way to doping and the cobalt side, like nickel, magnesium, and coat this part. And so that's why we make this lithium metal oxide just represent all kinds of lithium metal oxide layer structure. And this part is graphite. Graphite has theoretical capacity 370, but it's not enough for the batteries. So currently, the silicon anode, they can give the theoretical capacity 4,000. So it's 10 times of this current graphite anode. So that's why we can accomplish the target of to increase the capacity of lithium battery. And electrolyte is very important. And the first moment, and not many people, not many researchers focus on this, emphasize on the study of electrolyte. But actually, afterwards, they found that electrolyte play the key role in this battery, and they will ensure the safety of this battery, and also can ensure the long lifetime cyclability and rechargeability of this battery. And for the chemistry and between the electrolyte and electrode is also very important. So we call the solid electrolyte interface. That play the key role in this battery because all of the reactions started at the surface. So surface chemistry is the key issue in. We have to address this surface chemistry when we design the battery. And also the electronic and ionic conductivity of the electrode. And when we talk about the battery, and some people said, okay, we didn't do the good job because we didn't follow the Moore's law, and that is indicate we have to increase the performance, double performance every 2 years. But think about this is a chemistry, electrochemistry, and this multidisciplinary science, and that means we not have the electronic charge carry factor. We also have to include the ionic factor, and also all kinds of things. So that means the equation for us is not 1/2; it's 1/2 power several times something. So it's definitely is slower than the communication science. So that's I'm talking when we talk about materials. So this is the summary of currently available lithium anode materials. And graphite is here, and the voltage close to lithium potential. By the way, all of the voltage from now on is based on the lithium ion. So graphite is close to the lithium plating potential. So, and then they can give you 370 milliampere per gram. And the thing is, because it's close to the lithium plating, that means lithium can, if you discharge, overcharge this battery, and this graphite will go to very low voltage. That means the lithium will plating on the surface. So finally, we'll have some kind of a dendrites, and then we'll increase the internal shorting. And so that's why we want to increase a little bit. So we use different kinds of chemistry. So some is metal oxide. I will talk about metal oxide later. So metal oxide have a different mechanism for this one. Metal oxide has a redox reaction. So lithium can come in and reduce the metal oxide, not intercalate into the structure. Reduce the metal oxide. So make the metal oxide to the metal. We found is some amorphous metal also form on the surface. So for the alloy, like tin and germanium and silicon is here. Silicon has a really high capacity. Those is alloy reaction. So that means lithium into this structure destroy all of the structure. But instead of make some crystalline, and they have some like alloy, and this alloy structure is amorphous. So we never get a crystalline from this alloy, except one exception. There has one exception. Once you go to very low, and there has some crystal form, but that crystal is not rechargeable. So that means there has alloy reaction and redox reaction, and the intercalation for the graphite. And finally, there has some titanium oxide. This one is above this red color. That means this one is much safer. And those red means is HOMO of electrolyte. So below this 1 volt, and most of the case on the surface will form some solid electrolyte interface. Even you don't cycle this, if you do not start this cycling, once you touch this material into this organic electrolyte, some surface monolayer surface molecules will form on the surface. Some interface is good for the cycling, for example, graphite. And the reason why we can recharge this graphite because of this interface. They are really good interface and have the really high ionic conductivity. So lithium pass this interface easily. So that is to keep this graphite rechargeable. And those surface film also protect the graphite further corrode by this organic electrolyte. But some metal, some surface is not that stable, it's not good, and consume lithium. For example, silicon. And silicon has large volume expansion during the cycle because say 4,000 milliamp hour per gram. So how many lithium can sit into this silicon? It's around 4.4 lithium per mole of silicon. So they accommodate large amount of silicon. That means the volume will be expansion during the lithium insertion. That means always have some new surface exposed to this electrolyte. That means the lithium conception form this surface film continuously. And that means you lose some lithium because once you have the full cell and all of the lithium actually from the cathode part, and then you waste some lithium and forming this surface film. So that is the one reason, the irreversible capacity during the cycling. And this is degrading the lithium-ion performance. And for the anode part, this is talking. So for the cathode part, and we do not have many choice. Because see, this scan bar is from 50 to 350. And if you remember in the previous slide, and this one is scan bar from the 0 to 4,000. So actually, cathode is limited this capacity of the battery. Once we talk the intercalation, we always talk about the one electron intercalation into the structure. For example, lithium cobalt oxide. Actually, lithium cobalt oxide is only 0.5 lithium into the structure. And the lithium ion phosphate has 1 lithium into the structure. So that is the reason why the cathode cannot give the high capacity. And the lithium iron phosphate is very popular, and because it's for the low cost of the iron element, and also it's very safe. So lithium iron phosphate has thermal stability, and those lithium cobalt oxide if you do the calculation of a theoretical capacity, the capacity of the lithium cobalt oxide actually can give the 278 if you use 1 mole of lithium in this structure. But the thing is, currently we only can get 160. The reason is we cannot extract all of lithium from this structure. And the cobalt oxide in the delithiation phase is very reactive. It can react with electrolyte and release oxygen. So that's sometimes you can see the battery is if you have battery on the like my Apple, and one day I found that the computer is not actually flat on the bottom. And then I open the battery actually have some gas accumulate in the battery package. That is very dangerous because those is a flammable gas and with some organic electrolyte. And once you trigger this reaction, they will give the thermal runaway and explosion. So, I think it's in the past 5 years, and the most work on this lithium excess material. Actually, this is a material can give a really high capacity compared to the lithium phosphate and the lithium cobalt oxide. It can give the theoretical 250. This is a really very encouraging development and funding in this battery for the lithium battery. But the thing is, this material has its own disadvantages. Those materials also layer structure. The thing is, they put more lithium into the structure, so they call the lithium excess. So actually, this structure have a similar structure of this lithium cobalt oxide, but difference is they replace the cobalt, so lower the cost, but they put more lithium into this structure. So you can extract more lithium from this structure and give the higher capacity. So think of bigger, and you can use lithium air or sulfur base. That can give you really high capacity, theoretical capacity. So currently, we do some study of the lithium air. So one part you just use lithium metal, and another part we use oxygen as cathode. It's like a fuel cell. Instead, we use lithium metal as anode part, and that can give a theoretical capacity not include oxygen is around 11K milliampere gram. So it's not the same level of capacity. But the thing is, it's very hard because lithium metal is reactive. Oxygen is, once you have it's okay to do the primary battery. You can just let them discharge at one time. But when thinking about rechargeable, and they have some issue, the lithium peroxide is not that easy to reduce to the lithium metal during the charge part. The sulfur base is one company is already commercial with sulfur battery, and they can get the high capacity. And the thing is, they still have some issue about sulfur because polysulfur, the product of the charger products is soluble in this solution. So that means all of the products is once you discharge this material and those product is dissolved in this electrolyte, you're losing some materials. So then I will talk about I will pick some very typical example for this cathode part. So just open your mind, and those represent a very classic electrochemistry in this lithium battery. So first one is vanadium pentoxide. Why would I talk this one? Because this have a similar history of the titanium disulfide. This one has layer structure, and this is the first generation of the cathode because they have a really good layer structure, and the lithium can get in freely and get out, and they have the largest theoretical capacity when we talk about metal oxide cathode. They can have the theoretical capacity is 510 milliampere gram if we compare this vanadium 5+ to 3+. And they have the very interesting phase because once you include this lithium, and they have several phase change, and finally it comes to the lithium 3 vanadium 205, and then they cycle this phase several times. So this is because vanadium pentoxide is hard to give a really good rate capability. And then we're thinking about we can reduce to the nanoscale. So this is why we use electron spinning technology to make this vanadium oxide to the very thin nanorods. And they have orientation. So all of the z-axis actually is arranged on this direction. So it's easy to get lithium in and out. And so we short the diffusion distance. So lithium diffusion distance is shortened. and they have a 2D nanorods, so they can have a higher root capability. And the disadvantage of this kind of material is first the irreversible loss. So as I mentioned, they have a phase change in the first lithiation part. So that means they need to use some lithium to finish this transition, and then some lithium will permanent locate into the structure and not releasable. So that is the sum gives the irreversible capacity. And second one is low voltage plateau. And if you see this one is a sloping type. So that means this battery cannot give you like a stable voltage output. It is sloping. And also the voltage range is not that high. It's from 4 to 2 volts. And we really want to beyond the 3.5, like 4.5 to 3.5 volt. So the voltage range is not that great. And then we talk about this layer compound. This material is very important for the battery. I think it's the second generation on the current generation battery. Most of the battery use this layer compound. And the thing is, it's different from this cobalt oxide because we want to dope the cobalt side by other cheaper material like nickel and magnesium, and dope this cobalt side and increase the capacity, but lower the cost and give the better performance. So, so this is the layer structure picture, and show this is octahedral transition metal oxide, and that lithium located between the layers. So for this doping lithium cobalt oxide, and okay, so here is I want to mention this technique, and we can make this doped cobalt oxide have a rate capability. Because once you dope the cobalt side, you lose the electronic conductivity, and that actually results in the lower rate capability. So how to increase the electron conductivity? And we think about we can use the carbon nanotube ramping all of the particles together. And so those is single wall carbon nanotube can ramp all of the particles together and increase the overall electron conductivity of this electrode. So this is SEM image shows primary particles and finally combined with carbon nanotube. And those nanotubes actually very well dispersed into this particle structure. And finally, actually, we found they have a chemical bonding between those particles and the carbon nanotube. That's further enhance the conductivity, especially the electron transfer on the surface, because the carbon nanotube is on the surface. And so this is the comparison of the effective of this carbon nanotube coating of this material. And this is shows the capacity versus the cycle number. And we're testing at a different rate. C means discharge or charge in 1 hour. The C/2, that means we use 2 hours to charge or discharge. And 5C means we use like 12 minutes to discharge or charge. And then we find that this black one is primary, just the pure bare materials and in the electrode testing. And all of the testing actually, we testing in the coin cell configuration, and just like the bottom cell, and we use the active material mixed with the binder and the carbon additives, and make this electrode and testing in the coin cell configuration. And on this carbon nanotube one, and we didn't use any polymer binder because carbon nanotube is really long and they can wrap all the particles, so we don't need the binder anymore. And this blue and the green actually show this this carbon nanotube enabled electrode have the greatly improved rate capability. Because they have the 120 milliamp hour per gram, even at 5C. Compared, there's lost a lot of capacity at low at this when we use the just the bare material particles. And on this LD one, and this is a surface modification of these particles. I think I will mention this in the next talk to talk about how to further solve the stability and durability of the battery. And So for, next, I will talk about this lithium iron phosphate. Yeah. Okay. Yeah, I will finish this one. So this is lithium iron phosphate. It's a very famous material because they have a low cost. And but the thing is, lithium iron phosphate has a really low conductivity. That means actually in this paper, so good enough to publish this material in this paper, and he thinking this one is only for the low power application. But once you figure out actually after 10 years and MIT researchers found they can actually use the really high charge like 1,000 C to charge this material. So they can doping material by different valence of a transition metal. For example, in this case, we use a different doping to increase the electroconductivity. So this one I show this is pure lithium iron phosphate, and this is a CV plot, and show how they degradation. And then we doping this material and at a different level. For the low level is similar as this bare lithium iron phosphate, and at a little bit high level, actually, you can see the peak very sharp and the reversibility is really good. And then we dope it even more, and it's still good. But if we doping very high level, actually they have impurities. Second phase coming on in this part. So that means the doping level has limitation, but we can say this doping do increase the performance of lithium iron phosphate. So this is just a comparison of this different doping level with lithium iron phosphate. And we found this doping, the sample B has the best performance when we're doping this doping into the phosphate and oxygen site. And I think I will just briefly talk about this anode part. And this is just the iron oxide anode. As I mentioned, metal oxide has different lithium reaction, different reaction with lithium. It's a reduction reaction. So they can give the really high capacity, triple of a graphite anode. And this is the current available material. And again, here is the theoretical volumetric capacity, and here is the gravimetric capacity. And what's the actual? The reality is we didn't actually use all of the capacity of those materials. So that means we need to further actually improve the engineering and package to fully realize those potential of the materials. And this is, I just want to show this picture from the CEDAR and MIT. And they do the calculation, and they do the many slowlands of materials, and find what's the next material for, what's the next for the lithium battery. And of course, we want a higher capacity, and we want a high voltage. And there's not many material available in nature, but anyway, we can make the new material. So, and this is the major challenge. First, we need a new material, and for the electrode, and we need the stability. So, and then, but for the new, besides of the discovery of the new material, what we can do? And we can optimize those materials, can fully realize those theoretical capacity. And those I will talk about in next Friday. And this is also shows what happened on the electrode and the electrolytes. And both have to be improved. And I think, so this is the next talk. And I will mention about interface and the surface modification to improve the performance of battery. I think I finished here. And I put this sentence here because I think it's multidisciplinary science. And also I want this end this to study on the mechanical electrical engineering, because we need to use the battery. We have to make the real battery to power the car and for the great application. So thank you for your attention.
We have some questions? Oh, yeah.
So the question I have is that earlier in your presentation, you showed a slide which was showing the advantages of electrochemical storage system like capacitors over the different types of batteries, including lithium-ion batteries. But you kind of ignored that later on, and you stayed more focused on a comparison between different types of batteries. So over here we're talking about a need for a system which you need a high power density out of that. We're talking about wide operating temperature range. We're talking about applications in electronics which definitely needs a fast response. And most important of all, we're talking about a system which is friendly and green to the environment. So the question I have is that what portion of the investment of NREL or typical and usual research institute goes to do research on supercapacitors, and if you want to take a bigger perspective, what is the future you see for lithium-ion batteries comparing to supercapacitors, with respect to the fact that recently some countries, including Japanese, they started using supercapacitors in their transportation system, specifically bus transportation systems.
Okay, I think it's a large question, and I try my best to answer you. So first of all, and NREL, we do a lot of lithium battery research, and there is several researchers, I believe, is work on the supercapacitors, and but they have different applications. I personally, actually, I didn't do much on the supercapacitor. I only do a small portion of a supercapacitor because I think it is because we have a really good graphing and carbon nanotube synthesis and NREL. Those is actually maybe good candidate for the supercapacitor. So we only do that part of the research on the supercapacitor. And for the applications, I think it is very different because the supercapacitor, they absorb and deabsorption. So the energy density is pretty low compared to the battery. And also, they have a self-discharging. This is not a chemistry bonding the reaction, chemical bonding reaction. So they have a really, once you put this supercapacitor in the car, they have a self-discharging. And so the thing is, I think the good thing is we can combine the supercapacitor and the battery together. But the thing is, currently development and advantages, actually advanced development on the battery, they can increase the power. So that means if we can increase the power density of a lithium battery, we may not need to combine the supercapacitors into the system. But for the current available application like car, and they do use the supercapacitor, like you mentioned, some Japanese manufacturers, they do put the supercapacitors into the car, and also for the grid storage. And they put the supercapacitor because they can quickly release a lot of energy in the femtosecond and some sub-second. But the thing is, energy density is not that high. Yeah.
Just one more question. Yes.
As you mentioned, we are interested to develop new electrode materials for these batteries. So my question is that by developing new materials, are we interested to increase the intercalation capacity of the electrodes, or we are interested to change the electrochemical Fermi level of the electrode, which can be translated into the voltage? Which one is most important?
Both are important. So for example, this the vanadium oxide is intercalation, right? We can talk about. And the Oliver structure is also an intercalation. And once we want to intercalation, that means we are limited. Because most of the cases we only can have the one lithium, because the transition metal is, we only can have like one oxidation state change. For example, cobalt oxide from 3+ to 4+, and for the iron oxide 2+ to 3+. That means it's only one lithium in. And other chemistry can give the maybe can give the different features. So that actually can enlarge the capacity. That one is very important. So that is the reason why the MIT researchers predict some other chemistry. So they have used different like oxide, silicate, and sulfate. And they try thinking about, okay, what's the other chemistry? So they just predict. So they only calculate what's the potential once you use the lithium into this system. So it's not a lot, not only for the intercalation chemistry, it's also for other chemistry. As long as we have open structure, can make lithium kept into the structure, and then we can store this material, store the energy. So I think both are very important.
So also, do we have any challenge about electron collection or electrical properties of these electrodes?
Exactly. So I also mentioned electroconductivity and physical properties of this electrode is play a key role for the cyclability and the rechargeability and the performance. For example, high rate. Because you think about lithium come in and the electron release from the structure to the circuit. So that means the electron conductivity is very important, especially for the once you do the high rate cycling.
Thank you.
One more question?
Yeah, I had more of a general question. I noticed the takeaway I got from most of your talk is that it seems that the need for new materials was like the key driver in a lot of the enhancements that you showed. So many new materials for cathode and anode, you showed so many. In terms of enhancing the performance of these batteries, is there any room for any enhancement in the actual device physics? Or is now the trend going more toward needing to find some materials such as transition metal oxides, some of which have been also used in the OPD world in similar ways? Where do you see sort of the trend going for particularly lithium-ion batteries in terms of how we can see better enhancements?
Okay, so also, first one, new material you mentioned is definitely good, and secondly, actually, we didn't fully use the capacity of energy density of those known materials. We still need to improve how to use this material, especially once you go to the nano scale materials, and I think Professor Amy Prito will mention that. So once you go to down to the nano scale, and some properties is changed. So in that case, actually, we still have a larger room to improve this material, known material, and besides of discovering new materials. Yeah. Thank you.
Thank you. Thank you.